about the classification of dynamical systems. So after the toolbox, the scoreboard by Dominik.
It was better maybe without. Okay. Sorry? Okay, and now you're telling me that? Okay, that would be worse. Really, about the title, of course there will be change of plans. The change of plans because because the guy who gave this talk on Monday was very slow, and I'm not even ready to start the scoreboard. And of course, I will blame it to the organizers, because really, as you now know, there are 2 of us, so we should have 4 hours. And in fact, there are 3 of us, because the third one is sitting there, here. So, okay. You see, we didn't manage to do much, because this is a summary of the last lecture. So we work with Polish spaces, and we consider equivalence relations on them. And an equivalence relation is Borel if, as a subset of the Cartesian product, is a Borel subset. And we use, to cut the very long story short, Borel for means something computable by inherently countable methods using countable amount of information. So Borelness is good enough notion computability for us, of computability for us. So knowing that computability means Borel, we now turn to mathematical how to boil water principle, and it says that in order to solve problem P reduced to problem P prime, which you know how to solve, and then a contrapositive is that if to prove that P prime is impossible, find P that reduces to P prime, and you know it is impossible to solve. So what is now reduction? Let me recall this definition. So we have 2 equivalence relations on 2 Polish spaces, and we say that Borel reduces to F, even only if, by definition, there exists a transformation from one space to another, which is Borel. We only consider Borel reductions because Borel functions are something we can compute. This is the principle of computability we use, such that for every x1, x2 in X, x1 is the relation E with x2, even only if phi of x1 is in relation capital F with phi of x2. Sorry? YF, yes. So second error, okay. Somebody please keep account. If we reach 31, coffee for everybody. And my apologies for this and others. Keep pointing them. So now we have this definition, and with this definition we can define what is a smooth relation. if it reduces in this Borel way to the identity on the set of real numbers. And combining those two definitions, this really means that we can find a single Borel function on our space which provides a number for each equivalence class. This function gives us the number which is constant and unique for that equivalence class, meaning that we can classify. Okay? So this is the illustrates the first line of the boiling water principle, that to solve problem P, we can reduce, and we have our. And of course, if we want to prove that some equivalence relation is not smooth, then we should find. So if now E, we know that it is not smooth by, I don't know, some theory told us, and E reduces to F, then F is not smooth. Because if we could find a reduction for F, then we compose two reductions and contradiction. So this is the second part. So now we know few types of a possible equivalence relations, because we want to use this theory of equivalence relations to solve classification problems. So what is now a scheme of solving or assessing complexity of classification problems is now the algorithm is as follows. Find a Polish space containing representatives of all equivalence classes and test your equivalence relation. So your favorite isomorphism notion, because okay, we are talking about dynamical systems, easy. So naturally, so we want to take our family of the dynamical systems we are interested in. We should make sure that we find one Polish space in which they all sit. Sometimes it is easy, sometimes it is a little bit more complicated, but it is, I think, never hard task to do. And we have to make sure that every equivalence class has at least one representative, is represented as a point in our space. And then we say that, okay, our isomorphism tells us which pairs of points, because usually it is not true that we will take only one. If we can take only one representative for each equivalence class, and if we can do it in a nice way, then usually it means that we have reduced to the smooth equivalence relation, so the problem is solved before we even started to work. So we find these representatives, and then there are many representatives of one equivalence class inside our space. So they are equivalent in the sense of the relation, and we have now isomorphism relation on one Polish space. So we can try to test it, and of course the goal is to maybe prove that it is smooth, but actually we can do much more than that, because there are a lot of non-smooth relations. So we are really only at the beginning of the whole picture of what can happen with those equivalence relations. So now maybe the first question we would like to resolve is to answer whether our equivalence relation is Borel. Because this will tell you in principle that, okay, maybe there might be no, there might be no invariants because they are non-smooth Borel relations, but even though there might be no invariants, the fact whether a pair of objects belongs to my equivalence relations can be decided by some countable algorithm, because being a Borel set means that every Borel set has hidden inside a Borel algorithm to decide whether you belong to a Borel set or not. So if the equivalence relation is not Borel, then this is bad. Not as bad as it can be, because for non-Borel relations we have a lot of possibilities, but still. So to do that, we have to still introduce one more notion. So a subset A of a Polish space X is analytic. That's a definition. If there exists a Polish space and there exists Y Polish space and there exists B subset of this Polish space, and there exists phi Y to X Borel such that phi of B is equal to A. So this is a very common error to imagine that image of a Borel measurable set through a Borel measurable function is always Borel, not true. Although if you make this error, you are in a good company, because Lebesgue also did that error at some point. But it is not true. There is a family of sets which is larger than the family of Borel sets, and those are continuous images, Borel images of Borel sets. And in fact, you can say every Borel set is analytic, and in fact, A is Borel even only if there exists such phi which is injective. So Borel sets can be distinguished from all analytic sets by saying that you can find injective. They are injective images, and images are just analytic sets. So here the point is that usually it is super easy to test that all, and now, relation, the equivalence relation is analytic even only if, as a subset of a product, it is analytic. This is a very, very simple definition, very similar schema of definition to the previous one. And now it is extremely easy to see that in most cases, equivalence relations we are consider are analytic. So consider consider any manifold. I will give you an example. Consider any manifold. Consider now all homeomorphisms of that manifold, and let E to be a relation of topological conjugacy, right? So E is a subset of a space of homeomorphisms times the space of homeomorphism, and the pair of homeomorphism is there even only if there exists a third homeomorphism which conjugates them, okay? We all know that definition. But this definition tells us immediately that this is now the analytic equivalence relation, because we now consider a triple, the set of all triples of homeomorphisms, F, G, phi. So those are triples of homeomorphisms such that there exists, not such that there exists, but simply phi composed with F is equal G composed with phi. And then we prove that actually this is a Borel set. And now we project this set from the space of triples to the space of pairs by simply forgetting the third coordinate. And this proves that this is an analytic relation, right? Because we found a space of for compact manifolds, a space of homeomorphism is actually a Polish group, and we have this kind of a reduction we wanted. So in other cases, this is a very similar. There is a very similar reasoning. Of course, I skipped here some details, but this is more or less what you can do in many cases in order to see that yes.
It's clear that you get an is it clear that for H of n E is not an Borel? How do you see that?
No, I don't see that it is not Borel. This is not a proof of non-Borelness, because so now remember now there is a picture. So if I have my favorite Polish space X, then I have the space of analytic equivalence relations, and here I have the set of Borel equivalence. So it is always analytic. So it cannot get worse than that.
Okay.
But it can be. So now we are facing a question if it is Borel or so better and or analytic, right? And in order to prove that it is Borel, okay, we should. Well, usually you use a definition of a Borel set. If you can represent if you can prove that your equivalence relations must appear among Borel sets when you produce all Borel sets using your countable operations, then you are good. But if you cannot do that, then either you are not so good as you thought, or or it is impossible. Then if you hope that it is impossible, then what you should do? So the same type of a reduction we define between Borel relations, we can also define between sets. So now we say that in our setting, in those Polish spaces, A contained in Polish space X, B contained in Polish space Y, and we say that A is Borel reducible to B, so I will use prime because it's a little bit different relation, even only if there exists phi from x to y Borel such that x belongs to I, even only if phi of x belongs to B. And which simply means that the preimage of B through phi is A, okay? And now, if you find A, if you find that A is non-Borel, and A reduces to B, then then B also cannot be Borel, because if it would be, then its Borel preimage had to be Borel set. Contradiction. So now, in order to prove that, so if we want to prove that some set is not Borel, in particular, if we want to prove that an equivalence relation and we want to test, or we want to prove it if it is not Borel, so that's a question mark, that's our question. It is, the solution is find F subset of, maybe F is not good, some testing set in some space Y, not Borel, and find phi, a function from Y to X times X, such that a pair X1, X2 is in your, that Y is in your testing set, even only if the pair, well, phi of Y, let's call it X1 of Y, X2 of Y, is in E, right? So in order to test that our equivalence relation, so now I specialize this general definition to equivalence relations, right? So here I give you a solution to all your problems of finding that something is not Borel. Do this and you are done. And I want to be a co-author of everything you find by that. So the solution is very simple. You find your testing set which is not Borel. You find your Borel function which takes elements on your space, but it has this special feature that it takes sets, the elements of your testing set, it takes only to pairs in your equivalence relations, and nothing else from Y is mapped into the pairs into your equivalence relation. Okay? So I don't know why, but everybody's favorite. So now now I have to tell you what is this T, what this T could be, and I don't know why everybody's favorite set T is a set of ill-founded trees. So,
could you do a constant?
No. You somehow embed, right? It's like you want the preimage of E, right? Has to be T. And so you cannot do constant function because T, in order to be not Borel, it has to be not a nice set, right? It's a complicated set, and every element of this complicated set has to end up into pairs which are in your equivalence relations in a Borel way.
Okay.
So if you can do constant, then probably it's yeah. Okay. Okay, so now, so in some sense, all those problems philosophically are again about recoding. You have certain structures and you want to embed those structures into the families of your pairs of your dynamical systems. And if you do that in the correct way, preserving some properties, then you have your reductions. So let us talk about well, non-Borel sets. So okay, this we all remember, I hope. And yeah. So what we want to do is we want to consider, we take full tree of countable order. So what is a full tree? It is a bit easier to draw a picture than to state some definitions. So we take vertices, and the root vertex has countably many children. So we can index them by 0, 1, 2, 3, etc. Each of those guys has, again, countably many children. And you go on infinitely many steps, right? So this is the full binary tree. And then how you can encode a full binary tree is that what we do is we encode vertices, because there's a countably many vertices on each level. There are countably many levels, so there are countably many vertices. Okay, so if you know that the set is countable, you can enumerate them in such a way that no child has index lower than its parent. Right? We have this enumeration. Of course, we cannot enumerate first vertices from the first level, so we have to go something like that. Okay, we put this vertex always goes first. This vertex and this level, root. And then we enumerate first vertex from of the children, and then we can enumerate the second vertex of the children, but then we can enumerate the first vertex of the second level, return to the first level, and we make sure that all vertices are enumerated, but always what we know is that every vertex has to appear with some number, and if we see a vertex with some number, then all vertices which were above appeared earlier. Okay, this is this is the only demand we have from this enumeration. Okay? So now we have our set of vertices, and then what we do is that we look at, so we identify, okay, these vertices, now V is a set, is a sequence really, because vertices are enumerated. So we take into all characteristic functions from the set of vertices to the sequences of zeros and ones, okay? And say the full tree corresponds to the function which it contains all vertices. So full tree is now encoded as the constant one function. But now imagine that I take a subtree of the full tree, a subtree of this full tree, and if I take a subtree of this full tree, then this subtree is always determined by the collection of vertices. And by subtrees, I always mean that okay, a trivial subtree will contain only one root vertex, and say another subtree will contain only one edge and one vertex, but I can also take a subtree which is an infinite branch going through the vertices which are on this picture with 0, right? Indexed with 0. So so a subtree is a collection of vertices which on this picture gives me a tree starting at the root, right? Some subtree of this. So this selects, okay. This is like this is very similar to our usual, from a topological point of view, this is actually the same as shift spaces, right? We say the set of indexing sets and the finite alphabet. So the topology on this is the same as for the shift space, which means that two subtrees are now close, even only if the characteristic functions agree on some finite bunch of initial vertices on my list. Okay? So in this way, I have, because of course, not all characteristic functions in this bigger space are characteristic functions of subtrees. Sometimes they are not. But I can select a subset, so now I take tau, maybe tau is not, but the space trees is a collection sitting here. I encoded trees from the picture into sequences indexed by vertices. And at the same time, I introduced topology on this set. Yes? No. Okay. So once you select a set of vertices, and you know that it contains root, and you know that if, and the demand for the collection of vertices to define a subtree is that a vertex, if a vertex is in your set, then its parent is in this set. So every time you take a set of vertices of this way, right? If V is in the set which belongs to some tree, then the definition is that parent of V also belongs to the same T. So if you take a collection of such vertices, then of course you imagine that you all add all edges. Edges are only on the pictures. Edges are to help us to understand that this is a tree, not to, this is not a part of a mathematical definition. You don't, you just, yes? No. But a good news is that every enumeration with this property is good. So all you need to know that there is some enumeration. It's that doesn't really matter. So sorry? No, because they are codings which do not correspond to a tree. So imagine that, okay, this vertex always goes as V1. Imagine that at V1 I put 0, so this is automatically not a tree. No, but good news is that in this space, the set of codings for trees is really closed. Because if you are a tree, because what is happening? Assume that you have a sequence of trees, so a sequence of functions from this space which converges to something. And you want to know if this something is also a tree, right? So you want to test this condition. If I have a vertex in my limit sequence, then the parent of this vertex also has to be in my limit sequence with 1, right? But okay, my vertex has now a finite number in my enumeration. And trees are coming to me. And because those are trees, the parent of this vertex also belong, so my vertex now, from some moment on, I have to see in all sequences from my converging sequence of trees, because my tree is a limit. So it has to appear. But because now I'm being approached by trees, then the parent of this vertex also has to appear. So the limit will have this tree property. Forests are closed. What can I say? Now, excuse me, I didn't. Yeah, because now so now you have to, all the time we are doing silently one translation between subsets of the set of vertices and the characteristic functions. So now, if I want to see a subset of vertices which is not a characteristic function of a tree, which does not give me a tree, I simply take a subset which does not contain a root, and this is not a tree. Which is the same as to say that in my sequence encoding the subset, I begin with 0, meaning that the root is not there, okay? We are okay, you forced me to be formal. So trees is a set of these functions such that if, okay, please remember that par is a parent function. Such that if, and I have my enumeration, right? E of V is the number. So if I have now T such that if for some V, if for every V in T, we have that parent of V is also in T, right? Which means by using this in the terms of characteristic functions, if T of V is equal 1, then T of parent V is equal 1, right? There are two ways of seeing this all the time. One is a character, so because in order to have a topology, we prefer to view this as functions, characteristic functions in order to put it into this space, right? But if we want to talk about pictures, it's better to talk about sets of vertices, to see them somewhere on the picture. Is that okay? And the root is always there. Yeah. And the root is always there, which is the same as, well, not identically 0. Right? This is I exclude silently. Thank you, Jérôme, but this is kind of a silent agreement that empty tree is not a tree, right? And if it is not empty, then root has to be there automatically by this second condition. But thank you. Okay. Now, but please keep asking me questions if I want you, as many as you, to stay with me until the end on Friday as possible. So keep asking me questions. Okay, trees. So now we have, what we have? We have a space which is actually a compact subset of a Cantor set. Because this space 0, 1 to the v is topologically the Cantor set. So we have a space which is also a Cantor set. So that's a Polish metric space. We have topology on the space of trees. So any subset, any collection of trees may be Borel or not Borel. And now it turns out that we have to define, so now look at, again, it will be easier to look at the picture. Trees can go into two kinds. Well-founded and ill-founded. So what is an ill-founded tree? It is a tree which contains one infinite path, at least one infinite path. So tree is a set of vertices or a characteristic function. And this is an existential statement, right? A tree is ill-founded even only if I can find a sequence of vertices which always go down, right? And the path, of course, is a sequence such that if you see something on every element, the first element of a path has to be the root, and every other element see its parent before him, right? That's a path. Infinite path. Sequence W n equals 0, infinity of vertices such that W0 is the root, and for each n greater or equal than 0, the parent of Wn plus 1 is Wn. So this is infinite path. A sequence of vertices such that you start in the root and you go on going down, 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 down. You cannot. No, it's so okay. In fact, great intuition says that you cannot tell it in the Borel way. If you look into the collection of ill-founded trees, this is not a Borel subset of the space of all trees. Because you no, well, not every well-founded tree, but it's.
But if you put this in like
So there's the trees. Okay, this is trees. This is not a question about if trees are Borel, but this is a question about sets of trees if they are Borel. Okay, and the set of all trees which contain at least one infinite path. This is a set of which is not Borel. Simply because so philosophically, in order to decide if this is Borel, you will have to find a countable protocol deciding if an infinite path is there or not. But you have uncountably many paths to test, and in a countable way, you can only somehow search only for a countable set of paths. And so you cannot decide with this protocol. But this is not the proof. This is just the kind of explanation. I'm not going to prove that. You have to believe me or look into descriptive set theory by Kehris. Okay? No. Trees is a set of vertices. So I told you, a single root is a tree. This guy, those two vertices is a tree. No. It's good to make sure that we understand that the subtrees are pictures which are trees contained in this stuff, but not necessarily always going down. In this whole picture, the tree in the full tree is ill-founded for certain. Root.
always has to.
Yeah. So I defining a path. This is a root. So any then for the next element of the sequence, I have to pick one of those. If I pick this, I have this, and I have to pick one of those, and this is a condition written here that I am always doing this. Okay? Always a root. Always a root. Always the vertex, the first vertex. Okay.
Is the same result true for finitely branching trees?
No.
No.
No. Sorry? Yeah.
Okay.
The finite branching is boring.
Even if it has like some infinite branching?
Yeah, because it is then, I think, compact, right? If you consider, not all finite branching, but okay. I think you specifically need infinite branches. I don't know why, but this is my intuition here, right? But yeah, sorry, of course. Yeah. Koenig's theorem. Yes.
So trees as a subset of 0, 1V, is that open, closed, Borel? How nice is that topologically?
Trees is compact.
Trees is compact, so it's a closed
Compact
subset
set in
of
the zero, but
Okay.
the space is zero-dimensional, so this is a counter set because it is. Hey, I really like that you like the space. Very, very good. So okay. So now we can, we have our favorite, and actually, well, the only set which you have to prove that it is not Borel by hand. Because once you prove that it is not Borel, you can use this procedure over and over again to get more and more non-Borel sets, right? The only difficulty is in producing a decent function, the reduction. So let us let us now go through this. This will be really more like heuristic argument, not a full proof, but what you need to do in order to find such a reduction in a dynamical system category. So, okay, I think now I need some space. Okay, of course, again, you have to prove that, but for a moment, believe me that the space of ill-founded trees is analytic. Okay, so it is analytic, but it is not Borel, so this is something which we call complete analytic, or specialists call complete analytic, and now you have to do the following operation. You're given a tree, find a pair of systems. So we now imagine that we want to solve our favorite, solve our favorite classification problem by showing that it is not Borel, so it is hopeless to solve. So we want to kill our hope. So we take our favorite problem, we find this Polish space of systems where everything lives, and we want to use this method on the right-hand board. So if somebody gives us a tree, we should be able to produce a pair of systems in such a way that the systems are isomorphic in our favorite sense, because in topological, in dynamics, we have many ways in which we can consider systems as being conjugate or isomorphic. C1 conjugate, topologically conjugate, orbit equivalent, Kakutanie equivalent, many ways they are for that. Even only if we got a tree with infinite branch. So we are given a tree, and once we receive a tree, we should start building our pair of systems. And when we read through our whole tree, when we finish, we should have a pair of systems which are isomorphic exactly, even only if the tree we were given had an infinite branch. But we have to do it in a Borel way. So what does it mean that, so sometimes in order to do something in a Borel way, to stay on the safe side, you find a continuous reduction. Because it is much easier to explain what is a continuous function on the space on trees than a Borel function, I think. So what is now, what now will be a continuous function? Imagine that we are not receiving our tree immediately. We don't see immediately our whole tree immediately. Only somebody transmits to us 0-1 sequence encoding our tree 1 bit at a second. So of course, at the first second, he will say, okay, root is there. This is not a surprise, but okay, we start unveiling what is the tree. And once we know the root is there, we should do something. We should start constructing our systems. Now, somebody tells us now that the next vertex is there or it is not there. And upon receiving our information, we should immediately encode that information, whether this vertex or this is there, constructing our systems. Right? So this is like we are receiving more and more information about the tree, going along the sequence, and this information should influence our construction immediately, saying something more about our system we want to get in the end, but in such a way that if we get two trees with the same initial coding sequences, this characteristic function, up to some moment, then our constructions should follow the same steps. And this gives us a chance, if we are more careful, that in the very end, what we are constructing is a continuous function. Because we hope that if we have sufficiently many initial steps the same, then the pairs of systems we are constructing will be close to each other in the sense of our space. This is what we have to guarantee, okay? So in the remaining 3 minutes, let me say this, that it was Foreman, Rudolph, and Weiss who did it first for ergodic transformations, in which you can try to build, based on the first informations you hear from about the tree, you build Kakutani-Rochlin towers, which gives you better and better approximation. But maybe it will be easier to illustrate this by telling you how you can do it in the way we did it to do something about minimal counter systems. So now imagine that you are doing symbolic dynamics, but your symbols are now infinite sequences. So in fact, so each symbol is now an infinite sequence of zeros ones. So I have rows, but I have infinite columns, but infinitely many rows. And now I take a symbolic system of this shape. So an element in my symbolic system is now infinite matrix, right? Rows infinite in both directions, and columns infinite down. Okay. This is my space, and somebody gives me a tree, and I want to produce a subshift of this space. Now, what is the topology on this space? The topology on this space tells me that two sequences are close, even only if I look at them as matrices of zeros and ones. They agree more and more and bigger this central region, okay? So now somebody gives me a tree and tells me something about, oh, okay, vertex root is always there, so the first step is always the same, but then I learn whether I have some, the second vertex on the list, if it is in my tree or not. And this influences my decision what kind of a subshift I will see on the first two rows. Okay? So I start with a full shift, okay? Then somebody tells me about if the second vertex on the list is there, so I maybe restrict the first two rows or this or other way. I make my decision based on this information. Then somebody tells me, well, the third vertex of the list is on this way. So then again, this gives me a choice what to do and modify my definition for my subshift on the first three rows. Okay? And this procedure goes on, but what this procedure, at least one thing is now, and there are many, many details, we are very far from resolving the problem, but I have minus 1.5 minutes, so don't have a time to do. But at least I hope we can see one thing is now clear, that this is continuous. Because if two trees are the same, right, then my decisions which describe this region of my final subshift is fixed, and it will be the same for all subshifts in my construction. Okay? This guarantees continuity. No. No, here? I kill them.
You always have to have the root.
No, but the root means that I take a root, and it means that I start with a full shift.
I know,
root
but
is always there,
then
so
put me a periodic orbit in a tree. How you construct it?
But where you put your
I don't
periodic
know.
orbits?
I don't know. I think that
No,
there is no periodic orbit in your tree. Your tree.
On a tree, unfortunately, there is no dynamics.
No, I know, but when you transform in the subshift, you must have. Well, I think that you should have some relation with the subshift and the tree.
Yes, I have some relation, and this relation is by encoding what I see in the tree into the structure on the subshift, but my encoding is looking at the tree as a combinatorial object. It has nothing to do with dynamics.
Okay, but then you always have the infinite branch.
No,
I don't know. I'm not
at some moment
understanding.
I may finish earlier and do yeah, yes.
Sorry, I think there's two steps. One step is relating the tree to this shift, and then this shift is going to be related to the dynamic consistence problem, and we don't know about that yet.
Yeah.
So.
Okay.
No, actually it's great. It's absolutely great. Somebody stayed until the end of the lecture, and even so maybe now I should ask you some questions. It's like, but okay, this is the end of my lecture. Thank you very much for your attention, all remarks, and